Well, good morning. On this beautiful morning in Minnesota anyway. Welcome to this Conservation Applied Research and Development, or CARD webinar, which is going to discuss the lowdown on high performance envelope retrofits. Thanks so much for joining us today. I'm Mary Sue Lobenstein, and I am the Energy Conservation and Research Planner at the Minnesota Department of Commerce, Division of Energy Resources. In that role, I identify and analyze gaps within utility conservation improvement programs and coordinate and plan research to fill those gaps. The CARD program is a major tool of that work. With me today is Laura Silver, who is a senior state program administrator at the Department of Commerce, where she reviews utility conservation improvement program triennial plans and annual status reports. Laura was the Commerce project manager on this research and will be moderating the Q&A portion of the webinar. Our presenters today are Josh Quinnell and Lindsay Ginty from the Center for Energy and Environment. Josh is a senior research engineer with 13 years research experience in solar energy, heat and mass transfer, and energy efficiency. He was the primary investigator on the research that is being presented today. Josh is currently working on grid modernization efforts, including strategic electrification, solar energy deployment optimization, and using efficiency and other distributed energy resources to manage distribution system capacity. Josh's recent work includes HVAC duct leakage and retrofit sealing, condensing boiler efficiency, energy recovery ventilation systems, garage containment transport, transport, and residential furnace efficiency retrofits. In her role as research analyst, Lindsay provides data collection and analysis for CE's various energy efficiency research projects. She is currently focusing on analyzing energy efficiency in retrofit homes and in HVAC systems. Lindsay is a graduate of the University of Arkansas, where she obtained her bachelor's in physics with a minor in mathematics. It is great to have both Lindsay and Josh here for the webinar. Before we start, I'll go over some webinar basics, which should be familiar to a lot of you at this point, but all attendees will be in listen-only mode. We'll answer all questions at the end of the presentation, but as questions occur to you, please type them into the Q&A box and send them to all panelists. We'll do our best to answer all questions within the time allocated, but if we don't get to some, we will answer them after the webinar. This webinar is being recorded and will be available on the department's website, and the slide set from the webinar will also be available. This webinar is one in an ongoing series designed to summarize the results from research projects that are funded by Minnesota's Applied Research and Development Fund, which was established in the Next Generation Energy Act of 2007. The purpose of the fund is to help Minnesota utilities achieve their energy savings goal. About $2.6 million is set aside annually for the CARD program, which awards research grants in a competitive request for proposal process. Results from CARD projects provide utilities with data to enhance energy efficiency program designs within their conservation improvement portfolios. And as you can see by this pie chart, CARD projects funded to date have been in all building sectors, as well as some that cross multiple sectors. The subject of today's webinar is the residential sector, and we'll discuss results from a recent CARD project that investigated moving beyond weatherization to consider the next steps in envelope efficiency. Now I'll turn it over to Josh to start the presentation.
Thanks, Mary Sue. We have a lot of material to cover today and not a lot of time to cover it, so I'm just going to breeze through and get right into it. For those of you who don't know, Lindsay and I come from an organization, Center for Energy and Environment. We've been advancing energy efficiency here in Minnesota for almost 40 years. We focus on community and data-driven approaches. Let's move on. Our agenda today, really quick here, I want to give some background, some maybe necessary, unnecessary background on the building envelope and space heating. We'll specifically get into our objectives. What are we doing here? Our methods, briefly touch on how we pursued this research, and then we'll spend the bulk of today talking about our results before getting into some conclusions, recommendations, and future work. So to kick it off, What is the building envelope? Very simply, it's just the collection of things that physically separate the conditioned from the unconditioned space, basically the inside from the outside. In this project, we're going to consider the envelope as a bunch of components, these major components being sort of the attic, the ceiling, the walls, the doors and windows, rim joists, above and below grade foundation components. And then all of those components leak air, but we tend to refer to air leakage as sort of one aspect of the entire building envelope. And maybe not surprisingly, the building envelope drives space heating load. For those of you who don't know, it gets very cold in Minnesota. Our envelopes shield us from the cold. Their efficiency essentially determines how much energy our heating systems use to keep our buildings and our homes warm, or at the very least not too uncomfortable. And since it's so cold up here, we do spend the majority of our energy budget heating our homes, sometimes up to 80% for a single family home. And to do that, most of us burn natural gas to meet this load. About 2/3 of single family homes in the state use natural gas to meet the space heating load. Thus, it stands to reason improving envelope efficiency is the largest natural gas savings opportunity in the state. More broadly, if we consider the remaining third of our homes that are heated by electricity or propane, and the fact we have to cool our homes, improving building envelope efficiency is overall probably the biggest efficiency potential. In fact, it's probably very likely greater than all other residential efficiency potentials combined. So this is a really big deal. It also turns out to be a very hard and long-standing problem. So how have we gone about treating this problem in the past? Well, retrofitting building measures is an established process. Conventional measures that do this are often called weatherization. Mainly, we go into houses and seal air leaks. We add insulation to walls and attics. Sometimes we upgrade windows. We often add storm windows to older single pane windows, and we consider window treatments. These things are awesome. And there's been a lot of work done into streamlining these measures and making them cost effective, both in Minnesota as well as nationally. However, weatherization is focused on basically bringing the worst buildings up to a minimum standard in a cost-effective manner. That's not really high performance. In fact, while results vary a lot, savings are typically around 15 to 20% for these projects. They're large and good for sure, but they're only a fraction of what's possible in regards to envelope efficiency in a heating-dominated cold climate. So how do we move beyond weatherization? Well, the simple answer is we already know how. We just basically do more of it. Probably the most long-standing concept beyond weatherization is called the deep energy retrofit. These are sort of whole house projects that seek to overhaul all the systems in a house for very large savings goals on the order of 50% or larger. These projects aren't exclusive to envelope work, but especially in cold climates, the absolute savings of a DER are always anchored by envelope improvements. They bring the most to the table. But in practice, these projects are complex, often invasive and very expensive, and they're usually pursued by extremely motivated building owners who are driven by environmental and comfort-based decision metrics. So what's another perspective on high performance envelope? Well, this might be somewhat controversial, especially if you're involved in building new high performance homes, but I think current Minnesota new construction code is pretty good for single family homes, of course, relatively speaking. This table shows the difference between existing buildings, so say all those buildings before 1990, and current minimum code, as well as what I hope would be the future code. What I want to highlight here is the difference between the numbers in the first row and the second row. The first row is sort of an average. We just think of it as an efficiency value of the component envelope, of the envelope components for the homes built before 1990. The second is current code. So setting the actual values and numbers aside, what's important here is the values in the second row are twice those in the first row. Current code minimum basically has envelope components rated at about twice as efficient as existing building components. So if we agree that current buildings are relatively high performance, this means that old buildings need about a 50% improvement. In future code, that is going to get even harder, maybe 66% better than existing building stock. So recalling weatherization, which only gives us 15 to 20%, we need something more. In this project, we set a target of 50% to try to match new construction or get reasonably close. We call that a high performance building retrofit. Specifically, we want to see how we can apply weatherization measures, continuous exterior insulation, and window upgrades to achieve that target. So why, how do we move beyond weatherization? Well, there's lots of reasons for why, in addition to the raw efficiency potential. First of all, we should recognize that we are facing diminishing returns on lots of energy efficiency alternatives. We've already captured a lot of that efficiency. Maybe this would be required to meet future SIP savings targets. Maybe it'll be required if we're realistic about achieving our climate targets. Energy burdens, infrastructure investments, workforce developments, these are all strong motivators for pursuing this work. So that aside, what are our objectives? Basically, our objective in this study is to look around and see where we're at today. What are the opportunities and barriers of moving beyond weatherization, according to the stakeholders who are most likely to implement that work? What does it take to make a high performance envelope? What are the natural gas savings, the project costs, and the cost effectiveness? And how do those things vary across our existing building stock? So next I'm going to hand it over to Lindsay, who's going to describe briefly our outreach methods for this project.
Yeah, so one of the initial portions of this project was to interview a variety of stakeholders who would work in this market. So our methodology and goals were comprised of these two aspects. First, we wanted to identify the opportunities and barriers as perceived by the stakeholders. And based on their perspectives, we wanted to try to quantify potential savings, cost, and market opportunities for these projects. And how we actually did that is we compiled a list of stakeholder groups that to reach out to be interviewed, a key group of which was the contracting group, both general contractors and energy contractors, as those would be the individuals implementing this kind of work. But certainly the group's perspectives, as listed here, are also important as well, such as supply chain information or how real estate market values these kind of homes, for example. And so an interview template was created that was similar in content, but we asked targeted questions based on the stakeholder's professional background. And then based on the interviewee's response, we would tabulate the final information in both a quantitative and qualitative way. And then lastly, to round out our perspectives, we attended multiple webinars, seminars, and other learning opportunities to see both how people talked about these kind of projects in just a conversational way, as well as to see how others presented this information, much like we're doing today. So all of which were important in rounding out perspectives of these projects in various lenses.
Thanks, Lindsay. So the other part of our project was essentially a modeling exercise. And the goal was to understand sort of the variations in energy savings, costs, cost effectiveness of these measures across the building stock. The goal is to capture the real variations according to the building characteristics and performance data that we have so that we can actually anticipate the outcome of real projects across approximately 1 million qualifying homes in Minnesota. So I'm going to walk you through that really quickly with this sort of flow chart. First, we found all the specific data sets we could on Minnesota single family homes. This was largely based on home energy audit data, research data sets. Most of these were incomplete from the perspective of describing a whole home. So we only have some of the characteristics we're looking for. We call it sparse data sets. Some of the important parameters, though, that we find in these data sets are given in the bottom left. This is not everything, but some of the important ones. So our first step was having to assemble all that data, making sure all these data sets play nice with each other, same units, the definitions of the different columns and variables. Then we represented all this data statistically because that enabled us to sort of find all the correlations between each of these parameters. And ultimately, then we can statistically sample that modeled data into representative buildings. Turns out it took us about 1,000 buildings in order to recreate, statistically recreate our source data. And from that, we add basically geometry calculations based on typical construction details to make up a home as a function of these underlying characteristics. Next, we pipe that into a space heating model. We'll recalculate space heating loads on these homes as a function of their properties. And separately, we pulled in cost data from several sources to try to build up envelope projects. Those sources include RS means cost data, retail cost data, supplemented by program cost data and bids that we received recently. The idea then is we create these projects, that they create a measure. We can estimate energy savings from those measures. We also have the costs, and we can pipe both those through a cost benefit test. And ideally, this gives us a fairly representative perspective about how savings, costs, and cost effectiveness vary across the building stock. And then, of course, we can vary this for all sorts of envelope projects. So I'm going to get right into the results here by handing it over to Lindsay. We'll talk about our outreach.
Thanks, Josh. Yeah, so after talking to multiple stakeholders, we came across this first big barrier, which was the lack of awareness that people had for this kind of work. So stakeholders who were interviewed were asked if they were familiar with various types of retrofit. We asked them on a broad scale of retrofit projects like the ones listed here to try to understand what sort of information they were basing their responses on throughout the interview. We found that many stakeholders were familiar with passive house or being net zero, but not as familiar with high performance envelope retrofits. This was also reiterated through other learning workshops that we attended, but from our findings, we found that 68% of people claimed familiarity with retrofits, while only 52 to 58% could actually define or give examples of a deep energy retrofit specifically. About 50% of people were just unaware of the work at all. 18% admitted that they didn't know what we were talking about, and 12% just didn't answer the question. So we did give people a definition during the interview, and we kind of discussed and gave context to what we were talking about, and that was our final results for that. So basically, people just didn't know what we were talking about. The next common barrier was the lack of interest that stakeholders had in these projects. And this feature was more prevalent in the builder-contractor profession, and it was also a frustration expressed by stakeholder groups about that particular group. So we'll start with the contractors themselves. So during their interviews, the group never explicitly stated that they were uninterested in these projects, but they often discussed at length how impractical they were due to logistics, workforce issues, or cost. They mentioned that they would rather do easier projects that were not as complicated or had extensive timelines. On the flip side, other stakeholder groups who were unprompted about this topic would spend a significant amount of time during the interviews to discuss their frustration with the contractor group, because it was their belief that contractors don't like to learn new methods. They're all kind of the mindset, if it ain't broke, don't fix it. They don't like to learn about energy efficiency. Some stakeholders mentioned that there's very low turnout rate for learning workshops beyond mandatory ones. And we just wanted to point out that these kind of issues really resounded throughout other webinars we attended, pilot projects we reviewed, and discussed by other researchers on this topic. So it's really not a unique finding to our study. But lastly, a problem mentioned was that contractors don't generally promote innovative projects and technologies. So we wanted to bring these two barriers together and say that the lack of promotion is likely due to the group's lack of awareness of this type of work. So contractors overall were very familiar with basic weatherization work, but they didn't necessarily know about high performance envelope retrofits, and even question the practicalities of them. So these two barriers, the lack of awareness and the lack of interest, were really drivers in the misconceptions of other barriers that we found throughout the project, the most notable of which is the cost effectiveness barrier. So the last big barrier, and the most frequently mentioned amongst our stakeholders, was the cost effectiveness of these projects. So 55% of stakeholders reported this as a barrier, and the barrier itself, again, was prevalent through all lenses that we reviewed throughout the project. Another important note that we'd like to mention is that the stakeholders usually were speaking on behalf of their clients. So the stakeholders themselves mentioned that these projects were cost effective, they were worthwhile, but oftentimes their clients would shy away from them due to large upfront costs. Many stated that the cost of the projects just weren't feasible for the average person because the out-of-pocket expenses were just kind of extreme for them. And in regards to contractors, I mentioned they questioned the practicalities of these projects, and most of that stemmed from the cost effectiveness. Their belief was that basic weatherization is sufficient enough and spending high capital cost on excessive insulation doesn't have good payback periods. And so payback periods was a common cost effectiveness measure amongst stakeholders. Another one also mentioned frequently was aesthetical payoffs. So clients preferred having a new bathroom or a new kitchen remodel over an efficiency project just because they had visual payoffs. And the point is that cost effectiveness really has a different meaning depending on which stakeholder group you were talking to. And usually those meanings are different than the utility-based cost effectiveness measure that we see. However, plenty of stakeholders also discussed how there really isn't any rebate incentives for this kind of work. They discussed a lot about how if there were insulation rebates or weatherization rebates, that would really help mitigate the high costs that clients faced. And so I know this work by now probably sounds really humdrum, as nobody would care about high performance building envelopes retrofits, or they're complicated, expensive, they don't know they exist. But I can assure you there's opportunities for these kind of projects, and we'll get into that now. So the last topic to talk about from our outreach was the opportunities. So stakeholders were asked the question, do you think implementing these projects is an opportunity or barrier? And interestingly, a significant amount of stakeholders, 59%, stated that they were opportunities with no hesitation, but oftentimes they would fail to give specific examples of those opportunities. Even in the cases of those who said that it was both an opportunity and barrier, which was 27%, they still recognized the potential on a surface level, but still would just discuss the barriers. So based on our findings, very few stakeholders, 14%, found that these projects are just a barrier, but the barriers were the most commonly discussed. And this is kind of an important point just because stakeholders and professionals who spend time working and researching on these projects tend to understand their potential. However, the market's perception of the barriers associated with them will make the implementation of the projects difficult to overcome, and they almost outweigh the opportunities to be had. So we'll just talk about a couple opportunities. So we found that you can lower incremental cost if you pair this work with existing maintenance projects. So for example, if you wanted to add exterior insulation to your home, if you do that when it coincides with an existing siding project, you'll lower your overall cost. There's also an aesthetical payoff for that as well. A house with new siding is just a facelift for the house. All houses with new siding look beautiful and flashy. There's also home equity potentials. Real estate values net zero and passive house certification. So there certainly is potential to have high performance envelopes have real estate market value as well. And then there's also non-energy benefits associated with this kind of work. So if you have a tighter envelope, you'll have a more comfortable house. It will be warmer in the winter, cooler in the summer. It's not as leaky. You'll have better air quality. We talked about home energy or home equity potential, sorry. And, you'll also have lower energy loads since all the heat you put into the house won't actually leave the house, right? So there's certainly more in-depth discussion about outreach that you could read in our report when it comes out. But before we run out of time, I'll pass it back to Josh to talk about our energy modeling.
Thanks, Lindsay. And just sort of a quick bottom line on what we learned by reaching out to the marketplace. Basically, we reiterated that there are strong and long-standing market barriers, and there always have been attractive efficiency, alternative efficiency measures that have kind of historically relegated high-performance retrofits to the margins. I say that, but I also want to be let everybody know that there are people out there doing this work, and they're doing a tremendous job of it. Contractors, architects are completing these projects in Minnesota and elsewhere. I just want to mention they're just not doing it at scale, and then all the market participants we talk to are just largely unaware of what's going on in the background. So we can think about that in a couple different ways. Maybe in a positive light, because of their rare status, though, I think we likely can conclude that the perceptions of cost effectiveness are not actually based on a lot of real data and outcomes. This is also kind of borne out in the literature, which does suggest there's a high variability in cost effectiveness, but on average, cost effectiveness outcomes are relatively cost neutral. So kind of those things in mind, what can we do in this project? Well, we're going to engage our modeling work to try to understand cost effectiveness and focus on the perceptions of it versus what where we think we're at today. So what are the costs and anticipated outcomes of weatherization and high performance envelope retrofit measures, and importantly, how do they vary across our building stock? So first we have to start with the baseline. So we have 1,000 buildings in our model. We're trying to represent around 1 million buildings in Minnesota. Average annual load of this building stock looks to be just shy of 1,000 therms a year, which gives us a design load of around 45,000 kBTU. In practice, you expect this to go up and down, maybe go down, hopefully due to occupancy variations, behavioral differences, internal gains, solar gains, and that kind of stuff. Turns out a quarter of the building stock has an annual load greater than about 1,200 therm, which equates to a design load of around 55,000 kBTU. And then on the flip side, a quarter of the building stock has less than 800 therm and a design load less than 35 kBTU or 3 tons. Importantly, this is we've arbitrarily kind of set this benchmark at 1990 for homes that existed before energy code was taken seriously. So for our project, though, we're a little bit more concerned not about the overall loads, but actually what components in the building drive these space heating loads. So the next slide. So this slide shows space heating loads by envelope component. And this is in absolute units of therms. Here's a box and whisker plot that shows space heating loads. If you aren't familiar with this kind of plot, each of these box and whiskers, we have a thick line representing the median. We have the box, which at the lower end represents the 25th percentile, the upper end, the 50th percentile. Together, these are the interquartile range, about half of the building stock. And then the ends of the lines are the min and the max. And then in gray dots, we're showing outliers. These are basically statistical outliers. So we have a lot of those in our sample population of buildings. But what we can see here is that walls, infiltration, and windows are the biggest components to space heating loads in single family homes. I guess we can note here the outliers in those components as well as the attics. Specifically on the attics, we've done a really good job of adding insulation to attics over the years. So these outliers likely reflect buildings with little to no attic insulation. In these cases, you can see that it can be just as lossy as the other major components. And you get a sense for how older buildings that have been untouched by weatherization are easily capable of still having 2,000 plus therm loads. So after those major components, we have some of the other things that are not the focus of this project, including the roof and attic in that, as well as the foundation components and the rim joists. So what is our first step? The first step is to use our model to weatherize all these buildings. I want to note that when we say weatherization here, we came up with our own standards, typically lower criteria for engaging weatherization, and then more rigorous standards on what we expect out of weatherization. We have 5 measures here: air sealing, attic insulation, wall insulation, rim joist insulation, and continuous exhaust ventilation. The last is sort of an artifact of the fact that once you do several of these weatherization steps, the home is often tight enough that it needs some continuous ventilation to enable appropriate indoor air quality. The basic assumption behind this weatherization work here is that we should emphasize weatherization work more than more expansive envelope work. Turns out that this assumption may need revisiting later on, but we'll save that. So our project costs are based on regression fits to weatherization project data by building size and type. We estimate the costs from that work, and then typical air leakage reductions and the differences in the insulation values of the upgraded assemblies. I want to make note here that we do need weatherization on most existing buildings, even those that are partially weatherized. Basically, we can't get to our target of 40 to 50% space heating load reduction without some kind of base of weatherization to build on. To do so, for example, using continuous exterior insulation requires very thick assemblies and an even larger dependence on windows. So what does it take to do weatherization? Well, on the left, you can see the number of measures needed and the amount of building stock that needs a certain number of weatherization measures. We can see that about 75% of the building stock needs 2 or 3 of these measures. These are typically air sealing, attic insulation, and wall insulation. It's less common for a building to take only 1 or 4 measures, about 10% each. You can also see that very few buildings needed 0 measures or 5 measures. The 0 makes sense. If a home typically didn't need any energy-based weatherization, then it probably had low enough infiltration that it needed to add continuous exhaust. On the other hand, if you're a glass half full, you can see it's kind of encouraging maybe that we didn't need 5 measures very frequently. For example, maybe it's very rare for a building to be bad in all ways. If you're a glass half empty, you might see that, well, you did 4 measures, but you didn't need exhaust because your home was still so leaky. On the right side, you can see the cost distribution. We have the average cost in blue and then median cost in red. Again, these both are pretty similar. They come in around $4,000. They're about the cost of doing 2 or 3 weatherization measures. But you can also see on this distribution that it's highly variable, varies between about 1,000. In this case, I think we capped it at 9,500 for this chart. So what do we get from weatherization? Well, these are what the savings profiles look like. I have absolute savings in therm on the left and relative savings on the right. Again, median in red and average in blue. If we look on the right, average savings are about 19% and median savings are about 15%. In terms of absolute savings, this is somewhere around 200 to 250 therm. It's important here to reflect, to comment on the characteristics of these distribution. Notably, we have some very high savings outcomes from weatherization. You know, our average savings may be 20%, but we do see a substantial number of outcomes at 40% to 60%. Kind of anticipate what leads to this. We know leaky homes, no insulation. But we also have a fairly large population of buildings with very small savings, say less than 10% or less than 100 therms. And this is sort of a consequence of the methodology, sort of brute force approach to weatherize all buildings. In practice, with some optimization, we might choose to exclude some of those homes, for example, that were anticipated to have like less than 5% savings, because they likely have a very disproportionate outcome on our cost effectiveness. So one question we have is that, does weatherization actually change our priorities in which building envelope components we should go after compared to the unweatherized building stock? In short, no. Most of the losses are still coming from the walls, infiltration, and the windows in that order. So our next step, as Lindsay discussed earlier, is to try to understand what our opportunities are for taking it up a notch in terms of our envelope efficiency. In short, we want to add continuous exterior insulation on top of existing recladding projects. There's several reasons for this. First, there's lots of opportunities. We have a lot of buildings that have siding that is beyond end of life. Secondly, many of the costs that are shared between a continuous exterior insulation, or CEI for short, and a recladding project are shared. And in fact, this model is pretty conservative. I expect that in practice, there's probably a lot more cost sharing that could be recognized here. And third, exterior renovations have fairly good cost to value ratios. They make dramatic aesthetic improvements to existing buildings. People like them a lot, and they tend to recoup a fair amount of that in their home equity, which is an opportunity for us to expand energy work if it can be coupled with something that's very flashy, as Lindsay mentioned. It's also an opportunity to couple that with other non-energy benefits, thermal comfort being the main one. And the idea here is coupling these things to make a more attractive package to consumers who may be considering or maybe have told they need building siding maintenance already. Can upgrade this upgrade the security at the time of sale, either pre or post occupancy, or offer a more compelling package compared to other flashy, large dollar energy investments, such as solar photovoltaics or electric vehicles, which frankly are both outperforming envelope retrofits by orders of magnitude, despite probably similar or lesser net benefits. So the bottom line is we looked at several recladding project baselines. We built them up, put them through our model to try to understand what these costs are. We have a lot of stucco buildings, and it's difficult, so we had to spend some time there. Basically, a lot of things we can do with stucco. We can replace the whole thing, which is very expensive. We can demo and replace it with something less expensive, which is still moderately expensive. We can overclad it, which is similarly expensive to some of our other approaches. Most of our other cladding types can convert to vinyl, which is sort of a low-cost option, or fiber cement, which is a premium option. In this study, we did ignore asbestos and brick facades here due to their very low incidence in our data set, maybe about 5% combined. There'd be probably a different host of solutions for them. Bottom line, baseline varies a lot. At the high end, we have very expensive siding projects with median costs of $30,000. At the low end, vinyl is relatively inexpensive at less than $10,000. Again, we see the whiskers on our box plots. Things vary substantially across this building stock. So what's next? How do we leverage these projects to improve envelope efficiency? Well, we add continuous exterior insulation. Those siding jobs are our baseline upon which we can bundle CEI and ideally our weatherization and window work. There's a lot of insulation types that people consider for these projects. We've applied many of them here. And again, we try to build up projects around the steps that contractors would have to take to fit these into an existing recladding job. We have our standard rigid foams, our EPS, our styrofoam, our XPS, extruded polystyrene, our PIR, also known as polyiso. We have our EFIS, which is our synthetic stucco. EFIS is exterior insulation and finish system. I'll note here that this is the only recladding project that actually incorporates some substantial R value in its construction, in this case, 1 inch of EPS. But we could add more insulation to that process too. SIP is another project that works, structural insulated panel. It's essentially EPS sandwiched by OSB. It has nominally the same insulation value as EPS, but comes in fixed sizes, matching existing dimensional lumber. Then there's our closed cell spray foam, which we kind of apply exterior continuously on the sheathing. Then we have 2 semi-rigid products, mineral wool and something very similar to mineral wool made out of wood fibers. We look at applying these products and all the construction steps at different thicknesses, which entails doing additional work. Basically adding thickness to the insulation assembly lowers our relative insulation costs, but it adds a lot of ancillary costs. In short, the details can get expensive, and with especially thick envelopes, they can get very expensive. So we apply a bunch of continuous exterior insulation, and we make a substantial improvement in the insulation value of the exterior wall assembly. What do our savings look like? Well, we investigated 32 assemblies. The savings are essentially a function of the added R values, and we only have 16 different R values, so that's what we plot here on the curve. Curve shows basically the median savings for a given R value. That varies across our projects from 18% at adding CEI at R5 up to 32% for adding R24 of EPS. I'd add these are on top of our weatherization savings. And then the individual box plots show for a specific type of CEI measure how much that can vary across our building stock. Again, the variation across the building stock is huge by a factor of 3, which again is entirely dependent on the characteristics of all the buildings that make up this representative sample. The last thing I want to mention here is that if you look at the blue curve, you can see that there's a fairly obvious knee at around R12, beyond which we start to see significantly diminishing returns by adding additional insulation value to our envelopes. So the costs, the other important piece. There's a lot to unpack here, so bear with me. This chart is structured similarly to the previous one, but there's more information. In this case, I'm plotting the incremental project costs of this energy work as a function of the added R value of continuous exterior insulation. I have several different curves here of different colors to highlight the cost function for each type of CEI over the R values we investigated. Overall, median incremental costs range from about $4,000 to $17,000. Notably, again, with the individual box and whiskers, we can see the strong variation across the building stock. For each project, costs can vary by a factor of 2 to 4. And we can also see there's maybe some clusters of curves here. At the high end, we have our relatively expensive CEI projects that use wood fiber, mineral wool, and SIP. You pay the most for CEI assemblies constructed from these materials, basically. In the middle, we have our rigid foams in green. This is our XPS, our EPS, and our polyiso. And then at the bottom, we found the lowest cost projects in this study are EFIS and continuously applied spray foam. The EFIS makes sense. It's the only one that includes insulation to begin with. Hence, it has the least amount of overhead to simply increase that thickness of insulation. The real surprising result here is closed cell spray foam. The cost of these projects do undercut all other measures. They're also a little bit more invariant with thickness. As you can imagine, a lot of the costs associated with spray foam are in the setup, the takedown, and that kind of thing. So we have costs, we have savings, we can get into cost effectiveness. And I'm showing here one perspective on cost effectiveness for this project, which is looking at the median cost effectiveness results across the building stock for each project type. Turns out we have 465 project types. That's all our combinations of windows, CEI, and weatherization measures. We pipe that through the natural gas then cost model for the 21-23 triennium. Specifically, we're going to look at participant cost ratios using only the approved values for that model. So the first thing I'd like to draw your attention to is this chart on the right. We have our participant cost benefit ratio as a function of incremental project cost. In fact, let's look at the blue dots. We see all the way to the left, we have a dot that sits suspiciously close to 1. Turns out this is our weatherization work. I assure you this was a coincidence that our weatherization work came in at about cost effective, but it does set a benchmark for us. As you can see, as we add to weatherization, all our other projects in the blue dots reduce our cost effectiveness. And that is generally a function of the incremental cost. However, part of the benefits of this model is we can look at inside that building stock and look at those variations. And one thing I'm presenting here is the median cost effectiveness of essentially the 20% best buildings of each project. And if we do so if we look at the 20%, this is roughly 100 to 200,000 buildings out of our building stock, things improve remarkably. In fact, most projects with incremental cost less than about $15,000 have median participant cost effectiveness ratios greater than 1. Realistically, that's about $4,000 of weatherization work and up to $11,000 on CEI and windows. Realistically, that doesn't leave much for windows after you apply the CEI. But again, this reflects probably about 100,000 to 200,000 opportunities on single-family homes across the state. It shows that they can cost-effectively achieve very large natural gas savings. So let's unpack this a little bit and look at some project types in more detail. Here's a distribution of participant cost effectiveness for specific projects, consisting again of weatherization and then just continuous exterior insulation. The black curve is weatherization. One can see here, so there's a long tail on high cost effectiveness ratios. This is essentially all the low-hanging fruit that we get from weatherization, the worst buildings, and bringing them up to a minimum standard. However, once the building stock is weatherized, we see that all the other distributions are much tighter. And it's now because they have a very similar level of baseline performance. We've essentially removed one of the biggest variations driving outcomes in the building stock, which is their existing energy performance. Again, a surprising outcome here was how well closed cell spray foam performs from a cost effectiveness perspective. Here I'm showing 1 and 1.5 inches of spray foam applied in the exterior, adding about R7 or R10.5 in the red and blue curves. Found these are the best cost effectiveness ratios. Note they're very similar. There's only the very slightest edge to 1 inch versus 1.5 inches. In contrast to that, in green, I'm showing 1.5 inches of EPS, providing an insulation value of R6. For comparison, the average R value, bridged R value in our existing stock is something like R7.8, so even R6 is a major improvement. Lastly, I show the least cost-effective measure just for comparison is this new product. I'm not sure it's available on the market yet. Wood fiber insulation has very similar thermal characteristics to EPS, but unfortunately it's more expensive. There may be other reasons for pursuing that, but here applying 4 inches of that for an R16 envelope gets us this lowest cost effectiveness ratio that we saw in the project. So another thing we can do with our model is figure out what leads to cost effectiveness. First, we acknowledge it varies a lot, and a lot of existing approaches miss these variations by looking at average or perhaps only considering archetypes. But the statistical approach lets us see inside the building stock, makes us easy to identify opportunities on the saving side as well as the cost side. So the next question is, what do these buildings have in common? We'll save a lot of the details for another day, but some general findings are they're geometrically simple buildings. 1880s Victorians may be architecturally wonderful, but they're expensive to retrofit. Meanwhile, mid-century rectangular ramblers have easy exteriors to work on. The buildings tend to be a little bit smaller on average than the existing building stock, and they have slightly higher window area. In terms of performance, they typically have little to no wall insulation, as well as infiltration rates higher than the overall building stock. And from this, they have disproportionately high heating loads. So in summary, that's a lot of words to say they have lower retrofit costs and higher retrofit savings. I want to give a quick note about windows here. We did look at windows in this project. I don't have time to get into that here. Bottom line, windows rarely, if ever, improve cost effectiveness, but sometimes they don't hurt too much. They help with some of the more expensive envelope assemblies. There's probably more cost synergy between window replacements and what we've recognized in this study. So maybe there's a room to improve. Another thing to consider is that windows look more attractive when we recognize their high cost to value ratio. Like recladding projects, they bring equity to home. Consumers like them, which makes for a somewhat complicated relationship between building maintenance and energy work. So, talked a lot. I'm going to run through these conclusions really quick so we have some time for questions. But in the end, we've done weatherization in a relatively brute force, rigorous way. But it's shown that weatherization should be expanded. We have pretty good cost effectiveness from blindly doing this to our entire building stock. We should set higher standards and increase implementation. CEI at the time of cladding and coupled with weatherization can get us to 50% savings. Unfortunately, 50% meeting savings likely requires either window upgrades or energy recovery ventilation. We didn't model the latter in this project, but it's kind of a similar philosophy to adding exhaust ventilation to weatherization. Additional improvements yield a tighter envelope and energy recovery becomes viable, and it's big savings there. Again, cost effectiveness is complicated. It varies across the building stock. Has just as much to do with the building characteristics as it does with the efficiency levels of the measures. That said, while median cost effectiveness is less than 1, we have lots of cost-effective opportunities. At least 100,000 natural gas heated homes in Minnesota have a path to deep savings. I'd also like to reiterate that even at these diminished levels, these cost-effective opportunities likely are the largest opportunities statewide. And then lastly, these results are challenging. They've been difficult to interpret and present. And this definitely is not the final word, but I think there's a lot of uncertainty here. I think what we've shown by blowing up this process in a statistical way is there's a lot of opportunity here for further research and implementation. So some recommendations. Well, we have levers to pull on costs directly related to permit costs, sales taxes, property tax valuations. These are levels we can do to impact cost effectiveness. This project considered sort of the baseline bend cost framework, which limits the lifetime of these measures. It also doesn't include NEBs, which in many cases, prior research has shown have very high benefits compared to efficiency, which would obviously blow this cost effectiveness work apart. Our outreach work, getting back to that, has demonstrated that we really have to engage the market if we want to see this type of work accelerate. Namely, we have to engage the contractors, align incentives with their existing projects, make them want to do this, make them tell consumers about this. On top of that, we have to raise consumer awareness. People can't add an inch of foam with their siding projects if they don't know about it. We've shown actually also that the incremental costs for a lot of projects on some specific buildings are quite low. So this, contrary to previous thinking, should enable us to do a lot of pilot testing, essentially trying to validate what I've shown you here today and see if it's as viable as we hope it is. Lastly, there's so much in the pipeline, it's just impossible to list here. We took a very conventional approach in this project, essentially engaging the methods most similar to what contractors do today. I think this sets a fairly conservative upper limit, but there's so much in the pipeline. We've got custom products to lower labor requirements, a lot of computer-aided workflows, factory-built assemblies, all sorts of things that could come into play and make projects easier and cheaper if we can demonstrate the need for scale in this space. So I think there's a lot to watch here. In terms of our immediate future work, there is a lot of it. We can refine all this stuff by including more data. One thing we ought to do is include some optimization study to determine optimal outcomes for weatherization and CEI as a function of specific building characteristics. What I showed here was a brute force approach, which I think hides even more opportunities by trying to identify what is the best thing to do. One thing I didn't talk about is that all our lap siding applications added a rain screen, as we kind of determined it's a sort of a best practice from a building resiliency perspective. Basically pull the cladding away from the wall, make a drying space. This seemed like a good idea, but it does add costs without energy benefits. So we maybe ask if energy savings or cost effectiveness is our goal, do we really need that? There are other savings to consider. So things will look better when we add cooling savings, credit for lower future HVAC investments, improving demand response, flexibility of these buildings, and other NEB savings. We should also consider cost effectiveness for electric and propane heated homes, which are going to only be better than what I've shown here due to the higher fuel costs. Lastly, this one is especially important to me. There's a lot of attention on beneficial electrification these days, namely applying cold climate heat pumps. These results show that it's not that easy. In fact, there's significant weatherization and envelope work that will help in many cases, and in many other cases be required to achieve those goals. It's sort of a final word here. We put a lot of emphasis on cost effectiveness testing because it's how we compare things. We compare measure to measure. In the grand scheme of things, it's not that important though, especially from the perspective of incremental costs on major home improvements. The differences in cost effectiveness for most of the realistic CEI projects that I presented here are frankly just very small. They are in the margins of the larger projects. If we take a step back here and kind of reflect on our energy challenges, a lot of the other challenges we face, what I'm showing here, I think what we show in this study is that this is a massive untapped opportunity to make extreme levels of progress by instead putting our money into our buildings and our workforce rather than our fuel imports. And ultimately, the cost of doing that is in the margins. Thanks. Hopefully we've got some time left.
Thanks, Josh. That was a great presentation, and we do have time left. If you've not already done so, please type any additional questions into the Q&A panel and send them to us. Laura, do you have any questions for Josh or Lindsay?
Yes. All right. First question I just want to ask was a clarifying question that came up early on when Lindsay, when you were talking about the stakeholder meeting. So Nick Mark asked, can you describe the measures in more detail, what was actually being done to the home? Can you just clarify that, were you actually talking to the stakeholders about the elements that then Josh went on to describe in the model about continuous insulation and weatherization and window-based projects?
Yeah, so in our interview process, we didn't really go in extraneous detail like Josh talked about during the presentation, but we did kind of give them a little bit of context as to what we were talking about. So for example, we would just say, what are your opinions about adding 2 extra inches of insulation on the exterior, just as a kind of an example for them, because we were more interested in how they've just perceived the projects, how they know about the market themselves, what kind of items they see or projects that they pursue throughout the interview. So the actual detailed work about how the projects are done wasn't quite as important in the interviews.
All right, thank you. All right, here's a first question. If you were using the need for a recladding job as the point of entry to add exterior insulation, doesn't that considerably reduce the number of potential projects in a given year? Siding lasts for a large number of years. How many retrofits can we expect to have that we can add these measures to? Are these measures still cost effective in the absence of a need to replace the siding?
That is a terrific question, and you've spotted an important detail. Our best estimates right now are that buildings are undergoing recladding at about 2 or 3% per year. That is 2,000 to 3,000 projects per year right now as things stand. If we recognize that buildings are typically delaying recladding for all sorts of reasons, we might call it neglected maintenance. There are even more opportunities out there. 2,000 to 3,000 opportunities right now, though, is huge. It represents, for example, more than we're currently doing likely year to year in weatherization. And so even shrinking the opportunity down to just the projects that are viable on recladding is still has a huge potential.
All right. Thank you. Well, I'm looking at the time, and there are a lot of good questions, and but I think we have to turn it back over to Mary Sue to wrap up. So
Yeah, go ahead and ask a few more questions. I'll cut down my time for the closeout.
okay, great. Okay. Does CEE have programs in the pipeline that will translate this research to consumer or the contractor market? Potentially things that cities with sustainability plans can use to educate citizens and local contractors. Maybe you got at that with your last question, but do you want to expand on potential partnerships and avenues?
Well, just say you've spotted sort of the next step in this work. I think here we've shown that there is an opportunity to do that. And we can do so in a way that probably benefits everybody involved. And I hope that CE will get to do that. I'll certainly be a champion in my organization, but I think that the opportunity is well beyond that for other organizations statewide. And frankly, anybody in a similar climate, there should be some opportunity for us all to sort of engage the next steps and figure out how we translate this into viable programs.
Great. We've got a question about, did you consider cellulose in your study?
We did not. There's a whole host of things that we neglected to try to just, for pragmatic reasons, try to focus on projects that were largely similar. We found that adding insulation on the interior or adding, for example, a double stud wall to try to add additional cellulose was complicated and deviated enough from sort of the collection of project we consider that we didn't do that at this time. But again, I want to mention, we just focused on a subset of potential ways to basically improve walls, and adding cellulose in some capacity is yet another method we could consider.
Great. All right. Mary Sue, should I keep going, or do you
have one more? I wanted to do one more question.
One more question. Okay. All right. How about what time period is when you looked at cost effectiveness, what time period is cost effective measured over? And does a value of 1 mean cost pays back within that time? So
yeah, so that's kind of complicated. We basically use the cost benefits framework in the model with approved inputs, and they restricted our measure lifetime to 20 years. So when we say participant cost effectiveness of 1, it pays off in that lifetime. I will add, though, that the lifetime of these measures, especially insulation, is considerably longer than 20 years. And unfortunately, that's a discount we take in the cost effectiveness. If we're allowed to extend beyond 20 years, 25 or 30, we expect cost effectiveness ratios to improve substantially.
great.
Well, thank you. Sorry, Laura.
Yeah, go ahead. I pass it over.
Okay, thank you. Thank you, Laura, for handling the questions. I think we've got more questions to answer. We'll answer those offline and post those with the webinar recording. And thanks, Josh and Lindsay, for that great presentation. Really appreciate it. Here, I just want to I'll point out quickly that the webinar recording and final report will be available. The final report in a couple of months. The webinar recording should be posted within a month. But if somebody wants the slide set, they can email me and I'd be happy to send them the slide set. And thanks for participating today. We really appreciate your interest. There's no upcoming webinars scheduled at this time, but if you want to keep abreast to what's happening, sign up for the email list, and we'll send you information and updates and notifications when they are available. Please, in the meantime, contact me if you have questions or suggestions for the CARD program. And then there's also a survey to respond to at the end of this webinar. Please take a few minutes to let us know how we did today. Thanks very much and have a good rest of your day.